What we talk about in section 3.4? What's the main idea? So the big one is we've been finding local extrema and using that to help draw graphs, and we could get pretty good looking graphs. Now our goal is a little bit different. We don't need all the maxes and mins. We just want to know what is the biggest value, what is the smallest value. All right, so we call that a global extrema. Instead of finding what happens locally, can we find the absolute biggest or absolute smallest number? And if you go all the way back to section 1.4, we actually had this theorem that we skipped over. And it's called the extreme value theorem. It says if you have a continuous function on a closed interval, you're guaranteed to have a maximum and a minimum. So there is some biggest y coordinate and some smallest y coordinate, and there's an x value that when you plug it in, you get the biggest or the smallest. All right? So these are what we call global extrema. You do have to have a couple things like continuity and closed intervals. So, our typical picture. Let's say you have a function like this. So here's some endpoint A or B, and then A is sitting, we'll say it's 0. Right. What would be the biggest value? The biggest value happens at here. So if I plug in the number B, the biggest y coordinate would be that big value. What about the minimum? So I get to be right here. This would be my minimum value. So it's like I start here, do this. How many local extrema do I have? Or how many critical numbers, I should say that way?
2.
2? What are my critical numbers? 1. Right here, it's a local max. And then down here is also a local min. And technically, your book doesn't always say it this way. I would consider this a local min, and I would consider this a local max. And why would I want to say that? Basically, if you take all your global maxes, the biggest one, or sorry, all your local maxes, the biggest one is in the global max, right? And then, like, you have your local minima, the smallest one's the local min. But then the important thing is this is not a critical point if the endpoints. Critical points mean your derivative or 0 or undefined. That's not happening there, right? It's like the endpoints are their own thing. You don't have to have a 0 derivative and be a maximum at the endpoint. You don't have to have an undefined derivative to be a maximum. All right. So why do we need continuity? Well, if you had something like this.
Wouldn't have global max.
Yeah, why does it not have a global max? What does it mean to be a global max? This is where the terminology can be a little difficult or confusing. Yeah.
Since you can never actually get like close enough to the endpoint to actually determine the max.
The takeaway. When we say a global max, we say there is an input x that when you plug it in, you get the biggest y value. So you want to kind of think of it that way. Like when you find critical numbers, you find the inputs that matter, right? When we say we have a max or min, we mean there's an input that gives you this biggest value or smallest value. Is there an input that gets me up here? No, I'd have to plug in the number D, but I'm not allowed to plug it in because I have a bolt. So that means there is no maximum. Does that have a minimum? Yeah, that didn't change, right? Still has a min. So this is not continuous at the endpoint, but it does have a min. It doesn't have a max. What does it mean if we're not continuous and we're not on a closed interval? That just means all bets are off, we don't know. It may have a max, may not. May have a min, may not. So anytime the theorem says if you're continuous and on a closed interval, you're guaranteed to have a max and minimum value. Now it's guaranteed. There is an input that works. Once you lose one of these two, all we can say is it may or may not hold. You have to do more work. It's almost like that indeterminate type case. Basically, all bets are off. You have to do more work. Yes.
What about in the case that there's an infinite
Yep.
discontinuity?
What if your graph does this? I would say there's no maximum y. A maximum says take all x values. When you plug in this one, it's the biggest y coordinate you ever get. What happens here? If I pick this x value, that's not the biggest, right? So I pick this x value, I get a little bigger, but still not the biggest. There's no way to get to the biggest value because there's always something that goes up. All right, so anytime you have like an infinite limit, you never get to that value. Because you can't get there, because you can't plug in x and record y to infinity, there's always something that you never actually get to this maximum that you want to talk about. All right, so Berth last time you just say there's no maximum. There could still be a minimum though, right? Depends on where the graph is. If I say from here to here, it looks like there's a minimum, it's at one of the two endpoints. So again, it's anytime you break an assumption, it just means all bets are off. We don't know. So how do they decide? Well, you could have something like this. Something like that. That has a minimum but no maximum, right? You can't plug in a single number and get to that big value. All right. So let's do an example. Why do we care about all this? So today I was only going to do the background part, which is kind of, why do we skip it in section 1.4? Could you actually find the maximum then? In order to find the maximum, you need chapter 2. So we talked, this was the way you prove this, the reason it's in 1.4, it's only based on continuity. If you have a continuous function, you know you have a maximum there. Or these exist, but we couldn't find them. Now that we're in chapter 3, we actually know how to find them. And I'll go through the example, but a big takeaway is when you go to find these, global extrema should be easier than local extrema. So you always want to keep this in mind. What did we need to find local extrema? How did we determine if a critical point is a max or min or a local extreme value? First derivative test. There are times you can use a second derivative test, but you had to use one of those tests. So like the local extrema, say we need something like the first derivative test. If you're doing the first derivative test, what do you need? Go ahead and directly on that, please. You have to draw a number line, because you have to know when do you go increasing to decreasing, when do you decreasing to increasing. So first derivative test means you have to have a number line. When we find global extrema, there is no number line. Or in some sense, this should be less work. And it's because what do you need? You need critical points, and then you need function values. And part of function values is a technicality where you might need limits. We'll talk about that in the example. How do you decide, say your graph looks like this. Does it have a max and min?
Yes.
Yes. Is that an endpoint? Does it
No.
matter that I threw out the endpoints?
No.
No. How would I discuss whether that matters? How can I say this value here isn't bigger than this? Because if this value was bigger, I would say no max, right? How do you know what that y coordinate is?
You can find the limit.
Take a limit coming from the left, see what this y coordinate is. If that gives me the biggest output, then I can't have a maximum because I can't get to that value. So the idea is if you can only, we want the biggest y coordinate that you get to by plugging in a single x coordinate. If you have to take a limit in order to get to that y value, it means you can't actually get there, right? So if I need a limit in order to talk about this value, then it can't be my maximum. Here, I need a limit to talk about this value, but what do you notice when you find the limit? Limits are kind of like y coordinates, right? This y coordinate is less than this y coordinate, which means this one doesn't matter. My maximum was over here. How do we decide whether we have a global max or min? Where can we have a global max or min? Either at a critical point where the slope is 0 or undefined, and then at an endpoint. Are any other choices possible? So it's like we know where these can occur. Do I need to tell you it's a max or min by doing a number line? How can you decide what is the biggest possible choice? If we know all the places that matter, plug them all in, you have a list of numbers, right? The biggest numbers are max, the smallest numbers are min. Do I need to know that I go increasing to decreasing? No. If I plug in this y coordinate, this x value, I get a y coordinate that's bigger than this y coordinate, this y coordinate, this y coordinate. Those are the only 4 points that would make any difference. The biggest one works. Right. So all you do instead of drawing a number line, you just list out all the function values and then pick the biggest function value. Yes?
For the example you drew with the infinite discontinuity, if those endpoints gave you the same y, does that mean anything?
It could happen at more than one place. So the question is always what is the minimum y coordinate? It could happen at multiple x coordinates. So think like your sine function, you repeat that minimum value lots of times. That's fine, the minimum value doesn't change, what you plug in could happen more than once. Alright, so it's really talking about y coordinates. But in order for it to be a valid y coordinate, there must be an x coordinate. Alright, so let's look at this example. We're going to do this one on several intervals. So what do I need first? First we're going to look at the interval 0 to 4. But there's going to be lots of parts, we're going to do lots of intervals. What do I need first?
Find the critical points.
Yeah, I need critical points. Technically, I'll probably get tired of me doing this. I technically want the domain first. Why do I want the domain first?
I'm sorry, but it's really hard to tell, like, around the 0, if that's supposed to be bracket or parentheses, like, showing.
Close bracket.
Okay.
Why do I think domain might be relevant for any problem?
If you get a critical value that's outside of the domain, you get more.
Yeah, one, what my critical numbers need to be in the domain. Another one is something like this. How do you know this vertical asymptote? Try divided by 0, it's not the domain. Right. So if you want to make sure you incorporate behavior like this, always think about the domain first. What am I allowed to plug in? So, actually, I want to make this one more interesting and do this. So that has domain issues? No? Alright, we'll do the easier one. Domain's all numbers here. Good, I know the other one works nicely. I can only do the easy problem with board. Alright, so my derivative. Bottom part times derivative of the top, minus the top times derivative of the bottom, divided by the bottom squared. So I get what? X squared plus 1 minus 2x squared. So what is that? Minus x squared plus 1 divided by this. So now that we like to factor and do everything that we used not to do. Here, this is my derivative. So what are my critical numbers?
Positive and negative 1.
Positive, negative 1. If I plug in negative 1 or positive 1, the top is equal to 0. And there's nothing I plug in where I divide by 0. Thankfully, if you have a vertical asymptote or something, there will be something where you divide by 0. Alright. So if I'm on the interval 0 to 4, what do I need to plug in?
1.
I need to plug in 1 because it's a group number. What else?
0 and 4.
0 because it's my left endpoint. And 4 because it's my right endpoint. Do I need to plug in negative 1?
No,
Why not?
it's outside of your
It's
range.
irrelevant. It's not the interval 0 to 4. Right. So if you have a problem with a lot of parts, usually I do all this first. This is actually 90% of the work, it seems like. And then the rest of it is just plugging in values. What do I plug into?
The original.
The original. Why did I use the derivative?
To find the
Just
critical
to tell me the
numbers.
important x coordinates. But my goal is to find the biggest y coordinate, right? Where do I get y coordinates from? Y coordinates come from the original. So this would be 1 over 2. What about after 0, 0? And if I plug in 4, I get 4 over 17. Is it bigger than 1/2 or less than 1/2?
Less.
Yeah, less than 1/2. And bigger than 0. So what's the biggest number there?
Half.
1/2? And what's the smallest number?
0.
0. So my min is 0 at x equal to 0. Technically speaking, the min or max is a y coordinate. And then I always go a step further and say you get to that y coordinate by this x coordinate. That's relevant, especially for the word problems for the second half of this. Usually it's how much do I need to produce to make the most profit. That means you need to know the input also. What do you think the whole goal is for the word problems? If we can say, here's your function, here's the interval we care about, then you treat it exactly like this. If you can translate your word problem into this setup, then you can follow the exact same process. Did I draw a number lines or do anything? It was less work, right? Always remember it's less work to get a global max or min. Yes?
So finding the second derivative is completely unnecessary
We don't need
then?
second derivatives at all. The only time you might find a second derivative is if you want to do a second derivative test or something like that. But we also, we're bypassing the first derivative test the way we did this. So there are times in the word problem it's easier to do some other argument to make sure it's the max or min. But this one always works. This is like the fail-safe method. Alright, so what if I change the interval? Let's make it -4 to 4 open. Include 4 on the left, don't include 4 on the right. Now what do I need to do?
Now you need to plug in -4.
I need to plug in -4 because it's an endpoint. Can I plug in +4?
You have to find the limit.
What does this mean? This means I'm not allowed to plug in this number, right?
Mhm.
Because it's outside my interval.
You got tested anyway to see.
But I need to know what the y coordinate is in case it's the biggest one. So like I need to know, is it something like this or like this? So
You also-
what do we do?
You also need f of 1 again.
Yep. We take the limits, we go to 4 from the left. I'm not allowed to plug in the number 4, but I can plug in all the numbers right before I get there. So the way we say that is limits. See, we had a use for limits. I didn't believe us a while ago. What else? I need to plug in -1 and +1. Is this one allowed to be the max or min if it's the biggest or smallest?
No.
No. Anything that requires a limit, if it ends up being the biggest or smallest number, that means you don't have max or min there. You throw it out. So the nice thing about using a limit, because you have to take a limit, you know this one's off limits. Like you can't use that as your final answer. Alright, what do I get if I plug in negative 4? Negative 4 over 17. If I take this limit, it would be 4 over 17. If I plug in negative 1, what do I get? Negative 1/2. And this one is positive 1/2. So what's the min? What's the max?
Positive negative 1/2.
Okay. This one's the smallest. This one's the biggest. Then I could list what the actual limits are. Come on, that is way easier than what you did before, right? Don't forget that. Why do I keep saying that? I hear you have a test coming up. It's easy to panic on a test. When you panic on a test, you're more likely to like start drawing number lines or take a second derivative and do a bunch of work that you don't need. And then also, you're more likely to get the wrong answer because you can confuse yourself that way. Part C. What if I work on negative 1 to infinity? I need to plug in negative 1. If I plug in negative 1, I get what? Negative 1/2?
Mm-hmm.
I also need to plug in positive 1 because it's a critical number, right?
Mm-hmm.
And then what else? Can I plug in infinity?
Limit as x goes to infinity.
No, need the limit as x goes to infinity. So the limit as x goes to infinity of x over x squared plus 1. What's that limit?
Infinity over infinity.
There you go. We can go all the steps if you want. We already know the answer. Why? Degree 2 on the bottom, degree 1 on the top. What's the limit?
0.
No, 0, 2 did more work. But before, you have a rational function, bigger degree on the bottom, it goes to 0. Now, if you want to do that and convince yourself, just do L'Hopital's as many times as you need. You know, L'Hopital's will give you the same answer. Alright, so that's 1 over infinity, so I get 0. So what's the biggest and smallest?
The
I
biggest.
have negative 1/2, positive 1/2, and 0.
0 is the smallest and half is the biggest.
People are not good with negatives.
Oh.
0 is a little bit bigger than negative 1/2. It happens. Alright, what time is it? 1:50. We'll do one more. 1/2 to infinity. So what's f of 1/2? 1/2 over 1/4 plus 1. So 1/2 or divided by 5/4. So that's 1/2 times 4 over 5. So I get what? 2/5? And then f of 1 is 1/2. And the limit as x goes to infinity is 0. So what are my answers?
The minimum.
2/5 is less than 1/2, right?
Yes.
So that's the max. Why do I say there is no minimum?
Because it's a limit.
To get to the minimum, I had to take a limit, which means if that's the smallest value, it means I never get to the smallest place. By saying limit, it says we never actually get there. There are numbers really close to here, but we never get to the one value that we care about. All right. So anytime it's the limit value that gives you the smallest, you then say there's no minimum. If you were to graph this, your notes, it looks like this. where we know the max and min are the x equals -1 positive 1. Alright. Definitely, there's kind of two parts to the homework where one looks a bunch like this and then the rest are word problems. We'll do word problems on Monday.